Hi everyone, welcome to our next video for week 5. And here we're going to talk about hypothesis testing for a single mean where the population standard deviation is known. So notes, if you're doing the traditional method, your critical value is coming from table E or inverse norm, inverse normal. We're using a z-test. And your test value is coming from that z-score formula or from a calculator using the z-test or z-mean test function call. And you'll notice those function calls that are listed under the traditional method for finding that test value are the same function calls you're using over in the p-value method to find your p-value. So those function calls are going to spit out both. So if you're doing the calculator work, regardless of the method, you're going to pull up stat and go to test, just like we did last week. And you're looking for z-test. That should be the first option in your TI-84 menu. And then it should give you prompts for what you need to input. If you are using GeoGebra, you're going to want to do z-mean test. And it's looking for the sample mean, the population standard deviation, the sample size, the population mean. This is the value that's in your null hypothesis. And then the tail. And the tail is asking, is this a right tail, left tail, or two-tail test? It's looking for whatever symbol you used in the middle of your alternative hypothesis. So you're going to enter one of these symbols as your tail. What we're going to do is we're going to do 3 examples together. And I'm going to show you what this looks like with the traditional method by hand. And then I'm going to do traditional method and p-value method with a calculator so that you can kind of see how all those different methods work together. So let's go ahead and start with our first example. So for example 1, in Pennsylvania, the average IQ is 101.5. The variable is normally distributed and the population standard deviation is 15. A school superintendent claims that the students in her school district have an IQ higher than the average of 101.5. She selects a random sample of 30 students and finds the mean of the test scores is 106.4. Test the claim at alpha equals 0.05. So first thing that I see is I see the phrase test the claim. That tells me that I'm doing a hypothesis test and not a confidence interval. And you will almost always see somewhere in there, they're asking you to test the claim or very similar wording to that. So that's what tells me it's a hypothesis test. And now we're going to go through this problem and start picking off information. So they tell us that our variable is normally distributed. That's good news. They tell us the population standard deviation is 15. The very first sentence tells us average IQ is 101.5. So that's an assertion that the population mean is 101.5. And then the school superintendent claims that the students have a higher than average score. So what the superintendent is claiming is that the mean for her students is higher than that stated mean of 101.5. So this is telling us what our alternative is going to look like. She randomly selects a sample of 30 students, so they're giving us our sample size, and finds the mean of the test scores is 106.4. And that follows that discussion about a random sample. So we know that that's a sample mean. So this is an X bar. This is a claim about a mu. This is our sigma. And this is our n. Very last thing, they tell us alpha is 0.05. Test the claim at a level of significance of 5%. So we've got all of this information labeled in our problem. Now we're actually going to do that hypothesis test. So I'm going to do the traditional method for this particular problem. You can follow along and try the p-value method. We should get the same result and conclusion for the last two steps. The middle steps will look a little weird, but our hypotheses should match, our decisions should match, our conclusions should match. So step one is the same for everything. I need to identify a null and an alternative. I know it's a claim about an average or a mean, so I'm using that symbol mu. And I know that the superintendent claims that the students in her school have higher than average. That means greater than. So she's saying her students are greater than that 101.5. And the initial claim is that it's equal to 101.5. You could use less than or equal to here and you would be correct, but I always default to an equal sign in my null because it's the alternative that's the important part. And in this case, it's the alternative that we are testing. Test that claim. That's our claim. That's the superintendent's claim. For step two, looking at this symbol here that points to the right, that means this is a right tail test. Greater than means right tail test. So here, when I calculate my critical value, I'm drawing my normal distribution. This is a z-test. My mean is at 0. I know that I should have a critical value here. And this shaded in tail. And I know that the area in that tail is 0.05. What that tells me is the area in this tail is 0.95. And I can find my CV by using inverse norm. And inverse norm wants the area in the tail, specifically the left tail, and then the mean and standard deviation. If you are using GeoGebra, a similar function call, inverse normal, and it wants the mean and standard deviation first and that area at the end. But we're going to go ahead and pull up our TI really quick. Scoochie that over here in this corner. Ooh, not quite that far. And I know to get inverse norm, that second vars, and that's the third option in my distribution menu. So 0.95, 0, and 1. And I get a positive value, which is good. We know for right tail tests, we should get a positive critical value. So 6.4, 1.64. So that's the cutoff. If our test value is bigger than 1.64, our sample data is different enough from that stated population value that it's unlikely that original population value is true if our sample exists. So let's go ahead and calculate that test statistic. So for 3, we're going to calculate a z-score. I'm going to do this one by hand. I know that the z-score is x bar minus mu over the standard deviation divided by the square root of n. So for us, we've got 106.4 is our sample data, and 101.5 is our population value. The standard deviation for the population is 15, and our sample size is 30. So again, we're going to grab a calculator and plug that in. So let's pull our TI back up. And when I type this in, I'm going to type it all at once. And calculators are only as smart as the person who programmed them. It is important that you use parentheses when you have complicated expressions in the numerator and denominator of your fraction. Parentheses are your friend. So in the numerator, 106.4 minus 101.5. And then we're going to divide by standard deviation divided by square root of sample size. And I get the value 1.79 if I round to 2 decimal places. 1.79. I'm going to go back and mark that in my picture from step 2. Remember that our CV is 1.64. 1.79 is bigger than 1.64. We're out in that shaded tail. And we know that that shaded tail is the reject zone. So for step 4, we are going to reject the null hypothesis. Andrew can remember how to spell reject. So we are rejecting the null hypothesis. So step 5 is where we write our sentence. We're going to take all this information and summarize it. So first, I happen to know from that previous table that we saw, when I reject the null, I'm talking about there is enough evidence. So that's how I'm going to start my sentence. There is enough evidence. And then I look at my claim. If the null is my claim, there's enough evidence to reject. If the alternative is the claim, there is enough evidence to support. So in this case, there is enough evidence to support the claim. That, and then we summarize the claim from the problem. And our claim said a superintendent claims that the students in her school district have an IQ higher than the average. So we would say there is enough evidence to support the claim that the students average IQ is greater than 101.5, which was the original stated value. So we are supporting the claim that the average is greater than 101.5. You will notice that half of that came from the table that I gave you. So we know that this part here, there is enough evidence to support the claim that that's the sentence frame that comes from that two-way table from a previous video. I'll also have it posted on Canvas. The second half of that is coming from the problem. So this part here is coming from this part here. Students have an IQ that's higher than the average of 101. So I didn't actually have to come up with any unique wording. I just had to choose the correct sentence frame from the table and then pick out wording from the problem that completed that sentence frame. Ooh. Okay, so that is kind of a worst case scenario where we're doing everything by hand. We're going to do the next example traditional with a calculator and see how that helps us. So let's go ahead and move on to example 2. The Medical Rehabilitation Education Foundation reports that the average cost of rehabilitation for stroke victims is $24,672. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds that the average cost of their rehabilitation is $26,343. The standard deviation of the population is $3,251. At alpha equals 0.01, can it be concluded that the average cost of stroke rehabilitation at a particular hospital is different from $24,672? That was a mouthful. So this problem looks a little bit different than the last one in that last sentence says at alpha is 0.01, can it be concluded? So they didn't say test the claim, they said, can it be concluded? That's another way they're going to phrase problems that are asking for a hypothesis test. So that's another key phrase to keep an eye out for. Next step, we're going to go through this problem. We're going to pick off the wording. So first sentence, the MREF reports average cost is 24,672. That's a population value. That's not a specific group. That's just the average cost for all stroke victims in rehabilitation. So they've given us a claim about a population. And then we see in the next sentence, a researcher wants to see if that cost is different at a particular hospital. So there is a random sample of 35 stroke victims. That's our sample size, and finds that the average cost of rehabilitation at that hospital is 26,343. That's our sample mean X bar. And then it says the standard deviation for the population is 3251. That's a sigma. And then they give us our alpha value. The very last sentence, can it be concluded that the average cost at a particular hospital is different from? And different from means not equal to. That can be less than or greater than. So we now have enough information to run a hypothesis test. I have a claim about a population value. I have some sample data, sample size, sample mean. I have the population standard deviation. And because I'm asking about averages or means, and I have sigma, I know that this is a z-test. I'm given my alpha, and I'm given my alternative hypothesis symbol, not equal to. So let's go ahead and set up our traditional method test. So we know we've got a 5-step method. First step, state our hypotheses. We're testing claims about a mean, so I got to pop my muse up there. Next, I know my value is 24,672, and that same value appears in both the null and the alternative. And then I know my alternative is different from, and the opposite of different from is equal to, and we always know that our null can be equal to. I'm going to label my alternative as the claim because that is what that last problem sentence is asking us about. Can it be concluded that the average cost is different from that 24,672? Second step, that's our critical value. So we draw our z-curve. In this case, we're looking at this symbol here, and that tells me that the two-tail test, not equal to means less than or greater than. So I'm going to have a CV down here that's negative and a matching CV up here that's positive. We're coloring in our reject regions, and then we're going to find that CV again by using inverse norm or inverse normal. Because it's a two-tailed test, I'm going to take that alpha and cut it in half. And I know that 0.01 divided by 2 is 0.005. So that area there is 0.005. This area here is also 0.005. But I only need the lower bound, and I know the upper bound matches. So 0.005, 0.1. We'll pull up our TI calculator really quick. Second bar is inverse norm. And we get negative 2.58. I round that to 2 places. I'm going to write plus or minus 2.58 because I know that that negative value has a matching positive value. Okay, next step. We're going to use our calculator to find our test value. So that means going stats, going over to the test menu, and then we want a z-test. In this case, I'm given raw stats about the problem. So I'm going to click that stats button and it's going to ask me for some information. So here's how I'm going to write that. To show my work, I'm going to write the name of the function call. And then I'm going to list the information as I enter it in the problem. So first thing they're asking me for is that population value that we were given in the problem, 24672. The next is the population standard deviation, which we know is 3251. Then it's asking about the sample value, 26343. And then it's asking for that sample size, which we know is 35. And then the very last thing it asks for is, what is that symbol? And we know that it's a not equal to. If you're doing this on GeoGebra, it's going to be z-mean test. And the order of these numbers will be slightly different. So make sure you write down exactly what you typed in GeoGebra so we know that it's correct. But let's go ahead and type this data into the calculator and see what it spits out. So 24672, 3251, 26343, 35, and not equal. And then we're going to go down to calculate. And it gives us a whole bunch of things. It spits out the alternative claim, which I labeled H1, but we've been labeling HA, sorry. And then it spits out your Z test value and the p-value for the p-value. So I'm going to write that z-score down because that's what I'm using for the traditional method, 3.04. But I am going to make a note of that p-val over here. And I do label it as p-val. That's considered good practice because we use p for a lot of different things. And when we get to tests for proportions, that's going to get kind of awkward. Okay, so we're going to take that number and we're going to plot this in our picture. And we know that this is positive, so I'm looking at the right tail. And that cutoff is 2.58. 3.04 is bigger than that. So we are solidly in that red reject tail. So I know for my next step, I'm rejecting the null. I also know this with the p-value method because I know that my p-value, which is 0.002, is less than or equal to that 0.005 that I have in that tail. And that's what we're comparing our p-value to. So both the traditional method and the p-value method give you the same result. We should reject the null. And just like our last problem, we're rejecting the null, and the alternative is the claim. So we're going to go ahead and type our answer using the appropriate sentence frame. So we know there is enough evidence. Let me scoochie this over a little bit. Whoa, nope, that didn't work so well. Frowny face. Let's try that again. Here we go. So there is enough evidence that's coming from the reject in step 4, 2, and then our claim is the alternative to support the claim that, and then we pull the claim from the problem. Can it be concluded that the average cost of stroke rehabilitation is different from 24,672? So there is enough evidence to support the claim that the average cost of stroke, if I can type, stroke rehabilitation is different from, and then we put that value 24,672. Ooh. Okay, so it looks like a lot of work. I'm not going to assign as many homework problems because of that, but my hope is that after you've seen a few of these, it's going to feel very formulaic. I want to do one more with the p-value method, and from here on out, I'm going to use the p-value method because that is the more common method used in 2023. So let's go ahead and clear this and try our last example using the p-value method. So it says for a specific year, the average score on the SAT math test was 515. The variable is normally distributed and the population standard deviation is 100. A superintendent wishes to see if her student scored significantly below the national average on the test. She randomly selected 36 student scores as shown. At alpha equals 0.1, is there enough evidence to support the claim? So again, we're going to go pick through this, and I see that similar statement. Is there enough evidence to support the claim? So that's definitely a hypothesis test, because we know hypothesis test is asking about verifying claims. Once I know it's a hypothesis test, I start picking off values. So it says average score on the SAT math test was 515. So that's a statement about a population value. That's our mu. I said average. I know it's a mean. So this is a test for a mean. It says the variable is normally distributed, which makes us happy. And the population standard deviation is 100. That's a sigma. So a test about a claim about a mean, given the population standard deviation, I know I'm doing a z test. And then it says superintendent wishes to see if her students scored significantly below the national average. So that's a less than statement for our alternative hypothesis. And it says she randomly selected 36 student scores. So that's our sample size. And then they give us our level of significance, 0.10. You'll notice no sample mean, no X bar here. And that's because they've given us a list of raw data. So when we run this test, we're actually going to run it a little bit different. But let's write this down. I'm using the p-value method. So 4 steps. First is the claim. We're going to state our hypotheses. Next, we're going to calculate our p-val. And then we know that step 3, is our decision. And then step 4 is our conclusion. So starting with our hypotheses, claim about a mean, population value they gave us was 515. I default to my null always being equal, and I know my alternative is less than. I also know this means that this is a left tail test, which is good to know. And now we're going to use our calculator to find that p-value. So let's pull up our TI-84. Let's erase the stuff that's sitting on that screen. So we know we go stat tests. We want z-test. And now we're going to tell it we have data. And you'll notice it asks for those population values and then asks where we put our data. So we need to exit and put data in the list. So stat enter. I'm going to clear out that list 1 and type that data in really quick. I'm going to pause this video and I will be right back. Okay, so you can see I've got all this data in list 1. If I go up to that last data point, 504, you can see it's in spot 36, which is good because we are told we have a sample size of 36. So I probably got all my numbers in the list. Now we're going to go back to that stat test menu and run our z-test. So our sample mean is, or our population mean, our claimed population mean is 515. Our standard deviation is 100. Everything's in this 1. Frequency defaults to 1. And we want a less than. And then we're going to go down to calculate. And I'm going to jot down what that asked for us. So we did the test. They asked us for our sample or our population values. And then it asked us for sample data. Yes, and then it asked us for our tail, which we know is less than. And it's giving us a z-score of negative 0.358 and a p-value of 0.36, which is huge. And that makes sense because I know my z-score is very close to 0, negative 0.36. That's less than 1 standard deviation from the mean. That's pretty close to the mean. So I'm not surprised that my p-value is 36%. You'll also notice that it spits out that sample value, the sample mean, 509.0, which is pretty close to 515, particularly given that the standard deviation is 100. And our sample size is pretty small at 36. So this data is pretty variable, right? That's a pretty big measure of variation. We expect that this data spread out. And so getting a sample with a sample mean of 509 is not unexpected for a population with a mean of 515 and a standard deviation of 100. So this p-value down in our decision step, we're going to say our p-value is greater than our alpha value of point. Let's get our TI out of the way, 0.1. And that's going to tell us that we should not reject the null. The sample and the population value are not different enough for us to comfortably reject that null. And before I do my conclusion, there's one thing I forgot to do. And this is why I miss live lectures, because there's no one here to call me on it. I forgot to label my claim. We underlined it in blue significantly below the national average. So that alternative is our claim. You'll notice that's a pattern. That's more often than not our alternative is our claim. And now we're going to type our answer, and it's going to look a little bit different because in this problem, we failed to reject. So when we fail to reject, we say there is not enough evidence. And in this case, we're talking about our claim is the alternative. So there is not enough evidence to support the claim that and then we summarize the claim. So in this case, there is not enough evidence to support the claim that the student scored significantly below the national average of 515. Ooh. Okay, so we've survived the first run of hypothesis testing. Um, the next 5 videos, very similar. We're going to work through some examples a little bit quicker. If you have questions on what you've seen, feel free to send me an email or drop by my office hours. Otherwise, I will see you in the next video.